All right, everyone. This is Todd Alford. Been in technical support for a long time, so a lot of people know me. Extra fun fact about myself, I'm also an Eagle Scout, so do a lot of stuff outside. Today, we're going to talk about materials and boundary conditions, some of the troubles that they can cause, and kind of a different spin than you'll see for any of the documentation in the help. I've also got my colleague John here with me. So, John, you want to introduce yourself?
Yeah, sure can. I guess Todd and I have worked together for like 8 years now. We've been doing support solidly for 4. And my fun fact, rather than being an Eagle Scout, which I didn't even know that was until you said, is that we've just emigrated to Germany. So I'm now a Munich resident.
Nice. Crazy move. Balancing countries. I haven't done that one.
It's good. You should.
All right. Let me hop to our next slide and let's get after it. So let's go to update. I don't know why that's not letting me click.
If you need some PowerPoint tips, Todd, I'm here.
Somebody's going to have to teach me because for some reason I can't get. Well, let me switch to it.
Okay, I'm going to take control and present my screen.
Might have just gotten it? Or did you do that?
Too late. I've done it.
Okay, you take over. Technical issues on the Todd side.
Yeah, you can use CFD, but you can't use Office. Okay, so we're going to talk about the kind of basic setup of CFD. So carrying on from where Todd and James left off last time, where they focused on geometry and geometry setup. This time we're going to look at materials and boundary conditions, really kind of covering the basics and trying to make sure everybody's got a nice kind of foundation to move forward with. Before we start, I just wanted to mention 2 things. One is that CFD 2016 SB2 is out. It should update automatically, and we've just kind of listed here the things that have changed. I know quite a few people, I think, have had issues with trace particles and kind of graphics card issues. I think those should all be resolved now with the update, which is really nice. And also, if you're interested in seeing what's coming and helping us by testing our beta, you can. So you can download the 2017 beta. There's a link here which you'll be able to grab from the download folder later, and you just need to sign up, and once you've done that you'll be able to see what's coming, what's new, and hopefully you can help us by doing some testing. Okay, so over to you, I think, Todd.
Yep. So big points of today's discussion, I kind of want to at least give a glance over the material editor and give you guys a couple of quick tips. May be more useful for a lot of people that I just don't regularly see in practice. I also wanted to discuss material environments because it's just right down confusing. Do a little bit of a talk in devices because there's a lot available in CFD. Some people use it regularly, some people don't need it, some people should use it and they don't. So I wanted to go through a few of those things so that everybody can be a little bit more antiquated for all the capabilities that we have with materials. Using surface materials can also help make models a little bit simpler. And I also wanted to touch on errors, the uh-ohs we run into, and kind of how to think about it, how to approach it, and what we're going to be doing. Definitely reach out if it just completely doesn't make sense. Sometimes the errors get triggered in funny ways. But then we're going to pass it back over to John, and he's going to talk about some common mistakes. And is a model over-constrained? I always think about Goldilocks and the 3 Bears. Story from when I was a kid. I think most people are probably familiar. There's a little girl walks into the bear's cave and testing porridge and beds. It's too hot, it's too cold, it's just right. It's too hard, it's too soft, it's just right. That's kind of how you have to think about boundary conditions. We can't have too much or too little. You need to have the in and outs. And then John also wanted to do a little discussion on heat loads, which we'll get into some details with all of that. All right, shall we hop to the next slide? So there's two different environments. If we could change the wording so one wasn't an environment, I think that would be more useful. We have the scenario environment, just that little window, and then we have the material environment, the much bigger window. The scenario environment applies to everything in your current scenario. So if you wanted to run something at altitude, you would change what the temperature and pressure for that altitude would be, and then all of your materials will pull their base values for each of their properties at that temperature and pressure. Another case that you might use this is if you're doing a compressible analysis, because you want to be starting at, have all of your properties calculated at the local pressure if you're sitting in a pressurized environment. When we want to go over to the material environment is when we either need to have a variable or a fixed material, because it makes it harder to solve if it's variable, and it's also, I guess if you're doing fixed, we're making assumptions that none of our variables can change. If we have large temperature or pressure gradients, sometimes that's not a valid assumption, and we need to be in variable. To make it a little bit more confusing, we can also make it so that a particular material doesn't apply to the environment. So I'm sure that made sense to pretty much everybody, right? Let's
find out. I'm just going to throw up a quick poll. Okay, so we've got a poll open. I'll be honest, I'm probably going to answer no. But just to understand whether this makes sense to people, because I find this confusing, and I feel like a lot of people do too, so just to be 100% sure. Okay, so nearly everybody's voted, and we're at 50-50.
All right. That's fantastic, because I can never have this conversation just once when I have it on the phone. So that shows I'm running par. All right, John, you want to kick it over to me, and I'll give a little bit of a live demo here.
Yeah, let's do that. Cool.
All right, let's kick this over to monitor 2. And can everybody see my screen?
Yep.
Okay. And we're looking at CFD, not like my puppy or something like that we've done in previous webinars?
Yep, this time you got it right.
All right. Fantastic. So we have the scenario environment that's available when we right-click on materials and go to Edit Scenario Environment. Some of these things are available in the ribbon as well. But when we get that scenario environment, of course it popped up on my other monitor, and I've got to drag it over. This is where we can put in that temperature and pressure when, everything is sitting in the same scenario. If we've got something sitting at a plane, sitting on the outside of a plane and we're at 30,000 feet, we really want to take into account that 30,000 feet, and we can input it here. So now, when we made everything confusing, we go into this material environment. And we've got this checkbox, so by default, all of our materials that are sitting in a scenario are going to run off the scenario environment. But if we had a particular material where we had a very drastic difference, like let's say we were doing a heat exchanger and you've got air coming in at 200 degrees and we're water cooling it with water coming in at 50 degrees. So Now when we have the air, it would be at a different temperature. So we would be in the, what would that be, 333 Kelvin? So if you notice right now, when we look at the table for what the properties are, for air, there's constant for viscosity and conductivity, all of our other material properties. And when we look at the density, it can change by equation of state. And that's just your PV equals nRT. By default, it's looking at that 293 and your basic sea level temperature and pressure. But if I change that and I hit enter, if I go back into my air, oh, kidding me, I went to the wrong one. To the environment. Now we see that my density has actually dropped because I'm looking at a higher temperature. So that's going to be very important to make sure that we have the proper material properties being initialized coming into the model. And that's with it fixed. So if we don't have it under variable, then we'd still leave it at fixed, but I have a different density than I did if I didn't change the environment that's tied to the air material. I can then go to variable, and if it's a variable, as it goes through the system, the density will change based off of the temperature and pressure in the system. Hopefully that makes a little bit more sense. Should we kick that poll off again, John, and see if I did myself any justice or made things worse?
I don't know if you can. I'd say that you can't repeat it all.
Okay. So we'll leave it at that, and hopefully that gave a little bit more of an explanation. The other thing that I really wanted to kick off in showing you guys is the material editor. So this is where we're going to go and create our own custom materials. The most annoying thing is that you have to select a database to save it to. You can't modify the default database. But once we select, we're going to make My Materials. When we're selecting which property we're going to change over on the left, we have the entry points over on the right. I think all of that stuff is pretty easy to get across, and it's just making sure that you apply things and see them update over here. There's also a list so that we can select different materials and see everything that we have. And what I don't think anybody really uses is in the databases, by default we have the default and My Materials, so I have access to all the materials I create. But if John and I were always working on the same thing, how nice would it be when I create a custom material that John would be able to use it too? So one of the things I try to encourage some people when I know that you have multiple users is to create a new database and put that on a network shared drive, and then somebody else can just add the database from there. And then when you're using that database, everyone in the company can have use of all of your custom materials. Seeing where people are just sharing a support file and then everybody's trying to update their own My Materials. CFD has the flexibility, and it's pretty awesome to be able to pull from the same material database. And when you update it, the other person gets it. It's pretty awesome, and I think it's probably used by about 8 companies in the world because I put it in place for them. I don't know if anybody else does it or not, but it seems to always be a shocker. So I think that's a fairly good tip for people. Let's see if I can get it.
Todd,
yep.
Can I just interject for a second? So
yeah.
I just want to take a tiny step back. I'm going to say that a guy called Jim messaged, and he summarized what we took 10 minutes to share, I guess. And he summarized it really well, so I thought I'd share. He put, so the scenario is the default. The material environment can override it, and that override can be fixed or variable. Got it? I don't know. I thought that was a nice summary.
Yeah. Well done.
So thank you, Jim.
Yeah. You'll be presenting next time.
And
right.
You had another question on the same. Didn't you have to check the use scenario environment box?
So if I check that checkbox, then it goes back and it puts it to what the scenario environment was. If I'm, so again, if I'm creating something out in the desert and, you know, really I'm not worried about the ambient temperature here, oops, you know, at sea level, and I really want to know I'm hanging out in the desert and I need this to be, we'll just do it in Celsius and say that we needed it to be in 55, I can go back into my environment and use the scenario environment. Now I'm back down to that 1.07 density instead of the 1.2. But I can change it so that I don't need to pay attention to the scenario environment. I only do that if I've edited the scenario environment and it's valid, like we're designing something to be able to sit in the desert or at the North Pole, where we have a substantially different temperature. We're looking at the worst case scenario is generally the best way to design. So, you know, that's where you would put it in for the scenario environment, and it applies to everything. But in the case of a heat exchanger where we have two very different material settings, one's coming from, it's an exhaust gas and we're trying to cool it down, that needs to be sitting at the really high temperature, and then the other one we can leave attached to the scenario environment. You know, the heat exchanger would be sitting in a more of a room temperature kind of setting. I hope I got that. I may have gone over complicated.
I think that's fine, Todd. Thanks.
Okay.
Yeah.
Let me. I'm just going to end that and reshare it so that I can click through the PowerPoint. All right. So we talked about our environments. The next thing I kind of wanted to talk about was material devices. So when you're clicking on material type, I think the first two are pretty self-explanatory, where you've got fluids and solids. Is this a liquid gas? Is this an obstruction that I see? Wood, concrete, aluminum, whatever. Then we have these devices, and what these are really meant to do is when you have a complex system and you have parts that you're probably getting from another manufacturer. Like if you're looking at electronics and you've got a fan sitting inside your electronics box, you don't really care about trying to design that computer fan. You just want it to operate on the curve that we've got. You know, these are all of the devices listed. You can look in the help at all of them and see more about what they can do. But really what they do is they just make it so that you have to spend a lot less time on the analyzing of these things that are supposed to create a flow or impinge the flow. It's changing flow and heat transfer characteristics in the model by dropping it down to simple blocks. Something that I wanted to show, let's bring this up. So there is, you know, here's a little intro to CFD for AEC users. AEC users are one of the ones where I think they use the devices in things that you may not have thought about that readily. This isn't the page I wanted to be on. I wanted to go down to characterizing components. So this kind of shows you some of the different things, and you know, this link is in there. I think it's good for AEC users to see. You know, we can take some very complex geometry things, and that's not what we're really interested in using. So we can go down and we can characterize things down using a fan with a heat load. We can pretend that that's a whole server rack, because we're not trying to actually do any work with designing the server rack itself. So using devices to simplify analyses in areas that we don't really need to design, but we do need to have their representation. And when you're creating devices, I think it's also worth mentioning that we need to fill out everything that's in there. If you're not sure and you are missing data, you can always ask if can we just use the default. Put in a case. John and I are more than happy to look at it and think how much is that going to really affect you. But because what I'll see is with like a CTM, there's a theta JB and a theta JC. Essentially, that's ratios of how much heat is going to go to the case of a chip and to the board. A lot of times you will find that published by manufacturers, and in that kind of case, it is important to be fairly correct because you can put heat to the wrong area, and then it's not actively working the way that you intended. But if you're using that same assumption across the boards, at least you'll be trending in the right direction. Kind of my take on that. John, can you think of anything else that I should say on devices?
No, not at the moment. I mean, there's some kind of meshing specific stuff, but we're going to cover that next time, so I think that's okay.
Right. Yeah, I mean, the overall is you're going to save a lot of mesh, and it's going to save you a lot of runtime. The same thing with heat sinks. If you think about how many surfaces are on a heat sink, I can drop that down to a rectangle extrusion. That's pretty fantastic. So the fun stuff, material errors. Some of them are going to be fairly descriptive. If you look at some of these top ones that I have here, there's compact thermal model. Hey, this isn't attached onto a PCB. So some of our materials have specific rules. We need to have an air volume on each side of a resistance. You never want to have a device with a boundary condition applied to it, because the way that the devices are working, they should be pulling data from each side of the air and make sure that I'm putting in this amount of energy, I'm putting in this amount of flow, I'm causing this amount of a pressure drop. All of those things, if you put a boundary condition on a device other than a heat load, you can run into trouble. And the devices all have certain little nuances that you can look up in the help. And if you break any of those rules, usually you'll get some of these before you're hitting solve. I also wanted to throw out there, in 2016, we made it okay for compact thermal models not to touch air, because a lot of times people have a conductive thing where it's encased, so they don't really have air touching the compact thermal model, but CFD used to require it. It'll still give you that error message as you're going forward, but it will let you solve, and it does everything okay. That's kind of one of those false error messages. And then when we go into the, this little middle row of errors that I brought up, it doesn't really say what caused the problem. It just says, yeah, this is breaking some kind of rule. And if you see this when you're jumping into boundary conditions, it's talking about the device materials. These are where you can get some of these weird pop-ups as, not a cuboid. We specify that some volumes have to be just a block, or they need to have air surrounding them. And, they're less descriptive, but you know that it's pointing to a device. And then I thought it was at least bringing up the one's favorite error, the solver exited unexpectedly. Understanding when something is happening is what helps us as far as the troubleshooting, and can help you guys too. Because there's the processing results input and the processing restart BC data. If the analysis hangs, or you get that solver unexpectedly error, and it's at that line in the message window, that gives you an idea of whether it's a materials error and we need to look at the materials. Maybe we missed a definition, so basically you're going to end up with a divide by zero somewhere. We have an error if you put in a zero density, but I found that we don't have one if you have a zero viscosity, but we still will cause a failure. So there's some random nuances that if something was forgotten, you may get an error where the solver is just failing, or we diverge, and knowing when that's happening helps troubleshoot. Is it a material? Is it a boundary condition? And what can we do to at least find exactly where it is?
Todd?
Yep.
What's worth mentioning, I think, probably is that most of these, at least the top three here, almost always happen before you hit solve now. So we're kind of moving away from solver exit errors, which are a little bit abstract, to more kind of specific ones that do give you, a couple of steps to run through, which generally solve the problem.
Right. And that's kind of, you can see the ones that we've worked on more are at the top, and then I would call the middle row as more of a legacy. But it's even better than it was at legacy, because we used to not do anything. You just couldn't hit the apply button if you were back in 2014 or so. I don't know if 2015 would do the same thing. But I find that kind of interesting just from my history with the tool. And then I think I'm going to pass it to John.
Yep, that sounds right to me. Okay, so I guess what I wanted to kind of mention first is that when you're in CFD, you kind of work from left to right. So I'm just going to revisit the CFD interface. So we talked about geometry last week, and all we're doing is kind of going left to right, which is the kind of the process that you'd follow when you're setting up a model. So we've done materials. Now we're looking at boundary conditions, and then in a future couple of webinars, we're going to look more specifically at mesh sizing and then the solve window too. Okay, so just to talk about boundary conditions, there's a couple of very common mistakes, I guess, that we see often through support cases. One is over-constraining a model. So we need to leave CFD some kind of scope for mathematical error. And the other is assigning internal boundary conditions. There's one exception, which I'll talk about in a minute. So in almost all cases, these lead to one of three things. One is a solver exit, or one of the messages that Todd showed before. Which is okay because we know that something's wrong. One is divergence, which is less okay because it takes longer to find out something is wrong. And then the third one, which is kind of a nightmare sometimes, is that you get results, but they're not very good, and you don't necessarily know that if you've made a mistake in the setup. So you do have to be a little bit mindful of the approach that you've taken.
Yeah,
so just to kind of talk first about,
you've got to give the engineering checks after you've run a model. Make sure that you've got mass balance, energy balance. There are simple checks that you should run on every model. Never trust a machine. I saw Terminator.
Wasn't there a later Terminator where the machine was trustworthy? I don't know.
There was. I'm not trusting it yet. I'm still on Terminator 1.
Just on what Todd mentioned, actually, if any of you guys are going to AU this year, my talk is specifically on making sure that we have accurate models. So feel free to look that up and join if you'd like to.
Plug in.
Oh yeah. So just moving on a little bit, I thought I'd do like a really basic table. So the first kind of three rows here are okay. So having a flow rate on the inlet and a pressure on the outlet, or the opposite, are totally fine. It's more standard to have a zero pressure on the outlet rather than the inlet. I think the latter is a little harder to solve. It can take CFD a bit longer to do so. It's totally fine to have a pressure on either end, so you're giving CFD a pressure drop, and it'll then predict the fluid flow for you. We generally recommend using Advection Scheme 5 if you're going to do that. But what we need to avoid is the over-constrained scenario, so having a flow rate on the inlet and a flow rate on the outlet. That leaves no scope for mathematical error, and you can end up with results that aren't representative of reality.
Real quick, the other thing that I see sometimes, especially when people are getting started, they always want to, you start with something that you know. So I've got test data on this application. So we go and we put it in and we assign everything we know. And if we assign a temperature to an outlet and a flow rate and a pressure at the inlet, we're not letting the software solve what it's trying to solve. So, again, that goes back to that Goldilocks and the three bears. You don't want to underdo it. You don't want to overdo it. We need to have in and out and letting the software calculate something. Sorry, John.
Thanks, Todd. No, it's fine. I just feel a little bit disappointed. I had a Goldilocks and three bears image that I was going to pop up in a second, but I deleted it because you talked about it earlier. No, never mind. Okay, so once we've kind of got to those points and we've assigned, how the fluid is moving, we would then go a little bit further, and at the inlet, if we have anything to do with thermal, we would assign a temperature. We might assign a scale or humidity. And just to note that I guess I've had a lot of questions about this, that the way the output bar works. If you have a pressure-driven model, so you've got a pressure at the inlet, a pressure at the outlet, CFD will tell you that you have two outlets in the model. It's just how it works. So it always lists pressure as outlets, and it always lists flow rates as inlets. And so that can look a little bit confusing, but normally it's working totally perfectly. You might get a bit of feedback from your convergence plot. So the top plot here is a pretty sad-looking convergence plot with lots of saw teeth in it. I mean, really, you want something like the bottom plot. So ideally, it should be nice and smooth, and all of the different variables globally should be kind of tending towards a flat line, so a nice steady-state solution. And on the top, this is what happens if we over-constrain a model, and it can also take a little bit longer to run, which is never great. I thought I'd add a little tip too, because even if the model's set up perfectly, but you've got a poor mesh, you can also have a really poor convergence plot. So it might be related to something more than just over-constraining.
Yeah, that could even hit you on materials. Like if you have if you import a fan curve directly from a manufacturer, a lot of times I see a little bump in it, and because it's not smooth, you have two flow rates for the same pressure. And mathematically, the solver doesn't know what to do, so it bounces. Like you can run into all kinds of things like that.
Yep, exactly. I'm just going to pop across to CFD just for a second, just to really quickly hammer home like what's good and what's bad. So this model's bad. On the inlet, I've got a flow rate and a temperature, and that would have been okay, but I've got a flow rate at the outlet. So this model is over-constrained, and it's not going to give us good results as if I set up the model as flow-driven. So what I really wanted to have at my inlet, which I have here, is the same flow rate, the same temperature, and then a pressure at the outlet. So CFD now is able to have a little bit of mathematical error, and it will give me a pressure at my inlet, and that's the pressure drop of my overall model. Okay, so moving on to one of the other mistakes, internal boundary conditions. I guess boundary conditions are called boundary conditions because they go on the boundary of a model. I mean, I've worked with CFD for so long that seems obvious to me, but it is a really common mistake, and I can see why when you're setting up a model. So you can assign an internal boundary condition, and it can run okay, but you're probably not going to get good results. You might get terrible results, but you're almost certainly going to get a poor energy balance, which is often really important. The way we would assign a heat load or something internally, I'll show you on this model here. So the way I have assigned a heat load right now is to the volume of the chip, which is the ideal way to do it. What we could do, if we wanted to assign a boundary condition to this internal surface, which I have here as a temperature, we could do this, but we would need to suppress this part from the model. So the temperature would then be on the boundary of the model. And you can do that if the chip was enclosed in an air volume. As long as you've suppressed the part that the temperature is assigned to, that can work okay. It generally makes a little less sense than applying a heat load, especially if we...
On a surface heat flux might be a better example there, yep. Just that it's an apples to apples instead of the temperature.
Yeah.
There.
Yeah, I agree. I mean, here, either can work because it's underneath a solid. I guess the problem is if we've got a part in an air domain, when really we want to mesh the part. We want to assign a volumetric heat load so that we might enable radiation and it would work correctly. There's one exception, and that's when we run a smoke or fire type analysis, and we would have a scalar 1 on the top of that fire, so the scalar of the fluid changes, or the scalar value through that volume, but otherwise we always avoid internal boundary conditions. And I guess, Todd, you're saying that you've seen it fairly frequently, where instead of using like the internal fan material, which you just spoke about, we often see users assigning an internal boundary condition as a fan, right?
Either as a fan or as a flow rate, and if you've got a boundary condition between two air volumes, it's not going to be taken into account. The software will do nothing, and you're going to wonder where all my flow is. You need to actually use that material to cause a momentum source in the software.
Cool. Thanks.
Yep.
I guess I was going to skip over this slide, but I wanted to kind of include it. But I think I've almost covered everything. The only kind of thing that I wanted to mention really is if we are running some kind of thermal analysis, so we're adding heat into the model somewhere. I think users often forget that CFD needs some kind of reference. So like with the pressure, it needs to know where the pressure reference is. It also needs a starting point or ambient condition for the temperature, and that almost always goes at the inlet of the model. So we're never going to assign temperature at the outlet, because CFD needs to calculate that.
Yeah, and the scenario environment doesn't count, unfortunately. It'll just say that this model is being run without heat transfer enabled.
Yep. We had a question asking if we could talk about checking mass and energy balance. That pretty much summarizes my AU talk. And we are going to be talking about that in January, so I think it's quite a big subject, so we'll probably
well,
wait
we can
till
give just the basis of it.
Yep.
You want to pop open a summary file and show where that's actually recorded? I mean, that's probably enough to at least get people going with it, because this is, mass in should equal mass out. We should see where our heat loads are being put into solids, and then we should see the same heat coming out of the model. I don't know if that's the case with your model. It looks like it might have a funny balance.
So I guess that looks pretty okay. I mean, like looking at the energy out versus in, tiny number, that's okay. Heat transfer from wall to fluid matches the opposite. So, the energy being input is being extracted, and we have a good energy balance, as far as I can see.
Yeah, I was just looking at the M.C sub P, and, maybe we have something else goofy going on. This model wasn't run with the intent of being perfect. It's just kind of showing it off. But
yeah, the reason for that is mesh.
Right.
I'm pretty sure. I mean, it's pretty small, but it's going to be mesh.
Yeah, I guess it's only 0.014 versus 0.009. Yeah. It's 10% error. That's not bad at all.
Just for full disclosure.
Oh, and there's an inlets and an outlets section as well. Oh, yeah.
So, yeah, it's pretty insufficient. So just to kind of wrap up with the boundary conditions, there's a couple that I thought we'd mention in addition. Symmetry can be used if we've got a half model. So that my heatsink model I just had, I could have easily cut that in half and had a symmetry plane down the middle. What wouldn't have worked is if you take a look at my boundary conditions, I have slip symmetry on the walls already. And the reason for that is because I don't want friction on the walls. So the friction has been, or the boundary layer has been removed, so there's zero friction on the walls. And that's fine. But if we enabled radiation with all of these symmetry walls, which would act like mirrors to radiation, we would have something pretty similar to this image here. And you would see the error at the bottom. So it kind of repeats infinitely, and you would have some issues.
Yeah, and just to throw out there, this is actually James Kubley, one of our colleagues, gave me this from being at a museum where he's taking a picture through a one-way mirror, that's looking at another mirror, and you can see that there's only really 10 objects there, but it looks like there's millions, and that's what happens in the solver. It keeps trying to make this bigger and bigger matrix to the point of infinity. So I'm glad we solved out instead of crashing your computer. That's how it used to work way back in the day.
Yeah, things are getting better.
Yeah. Kiss your RAM goodbye was what happens if you do that.
And the last two things I thought I'd mention are just reversing boundary conditions. So depending on how you set up the model, I mean, thinking back to the last, what Todd and James presented last time, if we'd, I guess, had a solid part with a fluid inside it, when we assign the boundary conditions, so when we assign the flow rate, generally that would be pointing the wrong way. So here we could just press reverse normal and change the direction of the flow to make sure it was going in the direction that we wanted. So if you haven't kind of capped off the model like we recommend and you've built a solid around everything for a fluid to be created inside, you'll probably need to do this. And then the other is where we use, I guess, mass flow rates and the kind of total conditions. So when we assign, say, a temperature, instead of static, we could assign total, which would take into account the static and dynamic values. And we only really use this for compressible models, and the same for the unknown condition. So I guess quite frequently we might see models that are pretty simple like this with flow rates at the inlets, temperatures at the inlets, and then an unknown at the outlet. So we've got to remember that it isn't unknown, it's probably atmospheric conditions, so we should give CFD a pressure reference. So unknown conditions are really only used for compressible models.
One thing that I think is worth mentioning, John, can you hit the type drop down for boundary conditions?
Yeah.
So if you're looking at those top boundary conditions, the velocity, the volume flow rate, and mass flow rate, those are all averaging an even velocity across that surface. I thought that's worth mentioning because we do have the fully developed now. If you go to one of the volume flow rates.
Yeah, for velocity.
Oh yeah, even for velocity. So, that makes it so we don't need as long of an extension. If you guys actually look up that the equation to calculate it, it ends up being monstrous. If you were doing pipe flow, you'd need like 25 to 50 diameters extra. So I don't think that's perfect, but it can help. Got a case where we're looking into that right now. It's something goofy's going on.
Okay, so I guess that covers all the things we wanted to talk about. While we look at the questions that have just come in, what I wanted to do is just throw up the last poll that we have, just to see if we've answered enough questions or if you might like us to share something extra. If you do, we're going to need you to ask some questions.
So there is a question about if you were doing like that heat exchanger model that I was talking about earlier where you have air and water. We will not. You would have to look at in the summary, or you can look at it in results. I usually just do it there where I'm going to use a bulk plane and see what my mass flow is at my inlet and my outlet. That's my personal preference, but you can also kind of take notes on where your what the ID numbers are, and then you just need to make sure that each one of your separate flow areas is balanced.
Thanks, Todd. It looks like if we're going to talk about anything extra, we should probably talk about thermal boundary conditions. So we can. But if you could ask some questions to be specific about exactly what you would like to know, then we can definitely discuss it.
While we're waiting for a couple of questions to come in, I want to give one of my favorite descriptions for the problem when we do that heat flux on the internal surface is that essentially when we apply it to that surface, we can allow the heat flux to go either direction. And the surface is seen by CFD as being both fluid and solid. So does it push the heat flux into the solid or push it into the fluid? Or if it was two solids on top of each other, like John's model, does it go into the fins or does it go into the base? Sometimes you'll see that doubled. It just causes a mess in the energy balance.
Hey Todd, just to kind of look at some of the questions that we have. One is if we have more than one fluid, so we might have say, a heat exchanger with air and water. The summary file doesn't differentiate the mass and energy balance between the two. Is this correct?
Right. That's what I was saying initially, is you'd want to bookmark which ones are your water and which ones are your air to make sure that your mass balance is correct for each one of those flow paths.
And what CFD should do, I mean, it doesn't differentiate between the two, but what it would do is should give an overall energy balance still. So we should be able to understand if the energy coming in is the energy exiting. And if it isn't, we know that almost certainly where there's that kind of transfer between the two, that's where the problem is.
Right. If you add a material to a surface, quick thing I want to throw in about surface materials is you don't want them on exterior surfaces of the model. People will do that to say, yeah, I know that I've got like a housing that's this thick, and then try and put the boundary condition directly on that surface. But because the surface doesn't get generated until after we're solving the model, the boundary condition would bypass it. So I think the solver still exits when you do that, but I haven't tested it. And you should actually see a surface mesh in the results. You just have to hide an extra part. So I'm a bit...
Yeah, I guess the question though is, would we see a thickness if we assigned a surface material?
Oh, the thickness of it. I got you. Yeah.
Yeah, and I guess we wouldn't. It's a
Right.
mathematical model and it's not a physical model. It's there.
Right. We just
don't
show 2D elements for that, so it'll just be a shell of triangles.
Yep.
So I'm running a natural convection simulation with multiple internal compartments separated by metal barriers. Would I need a film coefficient for all internal surfaces? Oh, thank God somebody asked that. So film coefficients are meant to be exteriors on the model. We will calculate, the software automatically does air to a solid that's internal in the model. A lot of times people will try and put all those things in, but that actually double dips as far as the solver is concerned, because it'll try and remove energy from inside the model, and that's not what you want to have happen. You want it to transfer along until we get to the boundaries. So again, film coefficients, all surface boundary conditions are meant to be exterior boundary conditions. Other one that's worth mentioning for a film coefficient, if you think that there is going to be recirculation or are planning a model where you're not sure if this is an inlet or an outlet, putting a film coefficient with a very low value and a reference temperature is a way to have that recirculation go across a model without having any issues where you're locking a temperature on air leaving. So you don't want to affect that. You just want to affect air incoming should have the reference. I'm babbling. John, answer one.
No, you're doing fine. I'm trying to answer the questions by text as well. So one of the obvious questions to answer is that somebody can't see the site to download a slide. And I've noticed that address is wrong. So it should be CFD 19, and it's also not shown on screen. I just noticed. Oh no, it is. There you go. Okay. But it would be CFD 19 and not 17. So we'll change that before we put this online later.
And we were both working on this. Slap on the wrist, both of us.
Look at that. That is professional.
Nice.
That's for the YouTubers. Okay, so the other questions, there's not so many. How can I do CFD modeling for a data center? There's a lot on the website that Todd shared before, but if you've got specific questions, it might be worth logging a case with us and we can kind of talk one-to-one.
Yeah, and I actually do have I'm going to do a data center webinar, but it's still a ways out. It's not until next year. I think the next one we have planned is I was going to do a holiday special for you guys. But there will be a data center one.
Okay, we're running. We've got a few minutes left,
Yeah.
and there's quite a lot of questions. A variable temperature on the wall. Apparently, there was a problem with that in the past. I don't think there is now, as long as the part that the temperature is assigned to is suppressed and it's not an internal surface again, then that should be totally fine. Is it possible to define, a little bit off topic and tiny bit, but is it possible to define a surface inside the model and check that integral force or energy passing through it as a criterion for convergence? I'd say no, not at the moment. I mean, CFD has its own built-in convergence criteria that we can't change right now.
Well,
anything
we
else,
can't
Todd?
specifically locate it. Now, what did we get in for the questions? How to model a humidity source. That's something where you could, again, that would be like the smoke modeling, where you'd have that scalar input internal to the model. I think you might want to kick a case in and verify with your specific model that that's what I meant to answer, though.
I think you've answered it right, but it probably would be worth logging a case because I don't know if we've done it before.
Right.
I imagine it would work because it would be on a boundary still. But yeah, do log a case because it would only be a humidity value and it wouldn't necessarily be an inlet.
Right. Yeah, I don't know. Sounds fun. I'm in.
Yeah.
Let's check it out.
There's a question asking about checks with film coefficient values. I guess what I can show, and I'm kind of guessing as to what exactly the question meant, so feel free to change it if there's something else you wanted to share. But yeah, we could assign film coefficients. So say if I assigned one, so on my sidewall here, so some heat was allowed to escape during my analysis. There's a couple of values that we tend to use like really frequently. So say this is sitting in an ambient environment of 20 degrees C, that's going to be my reference temperature. And my film coefficient, if I had pretty still air, so just natural convection outside, my film coefficient is going to be about 5. If we knew that externally we had forced convection, so we would be extracting quite a lot more heat, we might increase that film coefficient to a value of about 20. I mean, these are assumptions, and we can't assume they're going to be spot on accurate, but it's a kind of nice guide, and it should give you a differential and something to compare different designs against.
Yeah, the big thing is to make sure that that assumption is consistent.
Yep. Okay. I think we pretty much answered everything.
Question about the CFD building HVAC. If you go to that intro to AEC or intro to CFD for AEC, there are actually, it's kind of a walkthrough of all of the different, or at least several different AEC type analyses. It's kind of a basic training for AEC users was the intent when that was put together by sim specialists. Give Mark and Tommy a plug-in. And myself when I worked there.
Okay, I think that brings us to the end of the questions, I would say. Thank you for all the questions. It's nice that we've it felt a little bit more like a round table. There was lots of contributions, which is really good for us.
Yeah, very much appreciate everybody coming in, asking questions. I know you're taking time from your day for something that may seem trivial to some of you, but very good to have everybody here. It is much appreciated from our side.
Absolutely. Okay, I think we'll wrap it. Thank you very much, everybody, and have a nice day. Appreciate it.
Yep.